I'm excited to come to you today to talk about partial derivatives. Partial derivatives just build on what we did back in single variable calculus around derivatives. They look a little bit intimidating at first glance. The notation is a wee bit different, but actually this is pretty straightforward. You got to basically remember one new fact, and you'll be able to do everything there is in the section. And again, with this one new fact, namely the idea of keeping one variable constant and allowing the other one to change, you'll be able to even do all of the interpretations that are involved with partial derivatives. Partial derivatives. The process of finding the derivative of a function with respect to one independent variable while holding the other variables constant is called partial differentiation. Each derivative is called a partial derivative. Note: the notation of partial derivatives that we are about to learn looks intimidating, but this is actually very straightforward and no more difficult than ordinary derivatives. Similarly, if you understand derivatives graphically, you should have no trouble understanding the graphical interpretation of partial derivatives. Partial derivatives. Functions of several variables have several derivatives, one for each variable. In the following example, we find these partial derivatives without yet having them clearly defined. Example 1. If f of xy is 2x cubed y squared plus 2y plus 4x, find the following. A. The partial derivative of f with respect to x of xy. And here we want to treat y like a constant. So let's write down our function. So we have f of xy, and that's 2x cubed y squared plus 2y plus 4x. And so we're going to treat the y's like a constant. So here, these guys are like constants. This is a constant. Conversely, we're going to treat x like it's a variable. So these are variables and variables. And so this tells us that the partial derivative of f with respect to x of xy would be the derivative. You'd have the 2, it's still going to be living there, constant. The derivative of the yellow stuff, because yellow is allowed to change, will be 3x squared. And then the pink stuff, y squared is just a constant, so it's just still chilling here. It's like, that's just a constant in that expression. Plus the derivative of 2y, that whole thing is a constant. 2 is a constant, y is a constant, and so 2y is a constant. So this would be plus 0, derivative of a constant is 0, plus 4 times the derivative of the yellow, which would be 1. So all told, we would have 6x squared y squared plus 4 for our partial derivative of f with respect to x at xy. B. Find the partial derivative of f with respect to y evaluated at 1, 2. Here, we're going to treat x like a constant, and then we're going to evaluate the partial derivative when xy equals 1, 2. So first, let's remind ourselves of what our function f of x is. So f of xy is equal to 2x cubed y squared plus 2y plus 4x. Since we're trying to treat x like a constant, all of our x's are now going to be pink. They're not going to change. And we're going to take the derivative with respect to y. And so the y's are going to be our yellow variables that are allowed to change. So this tells us that the partial derivative of f with respect to y evaluated at xy is, well, the number 2 is a constant, so it's not going to change. X cubed is a constant, so it's not going to change. But we have a yellow y squared, and the derivative of yellow y squared would be 2y. derivative of yellow is yellow, plus 2 times the derivative of y would be 1, plus 4 times the derivative of x is a constant here, would be 0. Or in other words, we have, what do we have altogether? 4x cubed y plus 2 for the partial derivative of f with respect to y at xy. The question also asks us to find this partial derivative, but now evaluated at 1, 2. So it's only after we find the partial derivative that we'll evaluate the function. And so this would be 4 times 1 cubed times 2 plus 2, which looks like a funny way of writing 10. We don't know what this 10 represents, but we will talk about that shortly. Interpretation of partial derivatives. The graph of z equal to f of xy is a surface in space. Here's the short version. The partial derivative of f with respect to x is the slope in the x direction, and the partial derivative of f with respect to y is the slope in the y direction. The long version is as follows. If the variable y is fixed at y equals y naught, so fixed at y equals y naught, that would be right here. And then z equals f of x comma at y naught is a function of one variable. You'll notice a function of one variable. It's this curve right here where the plane and the surface intersect. That is, the graph of this function is the curve of intersection between z equals f of xy, that's the surface, and the plane y equals y naught. The partial derivative of f with respect to x at x comma y naught represents the slope of the tangent line to this curve, which means the slope of the surface of z equal to f of xy in the x direction, or the rate of change of z in the direction of x. Okay, so you're talking about slopes, slopes of the tangent lines. Those would be these tangent lines here that are tangents to the red intersection lines. And we'll look at an animation of this in a moment. Before we go there, similarly, the partial derivative of f with respect to y would at x naught comma y, notice here it's the x that's fixed, okay, represents the slope of the surface z equals f of xy in the y direction, or the rate of change of z in the direction of y. And so again, we have this intersection line where the surface and that's not a great intersection drawing. This intersection line, I think that was good. Intersection line where the plane and the surface intersect, and then we could ask, what is the slope at some point along the curve? And so that will be our partial derivative. Let's look at an animation to try to understand or better understand the partial derivative of f with respect to x. So first of all, let's focus in on this intersection. So we have a surface, kind of this mountainy orangey thing, and we're going to intersect that surface with a plane that's formed when we hold y constant. Remember, partial derivatives require that you hold one variable constant. So we're going to hold our y constant, and when y is constant, that is going to generate this plane. So this is here's my plane that's being formed, right? And this is the plane when y equals b. And if you changed the b, it'll change the plane, right? It changes the intersection spot. So we're going to let y equal constant, and then we're going to ask where does this plane kind of cut through the surface? You can think about it like it's a cross section of the surface. And so the plane intersects along this curve here. Let me erase the picture and basically say the same thing again, because this isn't difficult, but it is pretty important. So let me change my angle. You can see it a little bit better. So I'm gonna change my angle. I'm gonna change my plane. So here I have a different plane. I've cut through that surface, and I've got some plane here. And you can see that plane. We could ask what is the profile, the cross section? Imagine you're cutting a watermelon or something like that. What is the shape of the slice? So here, the shape of the slice is this black curve. It's kind of crossing over. I think I can hide the surface. It's just the black line that's here. So the black line is kind of the profile line when we slice through at various values of y. So we fix our y, we slice through, and you get this black curve kind of slice. And so then we could ask, well, what's the slope along that line? And so just like we did back in Calc 1, we want to find the slope of these tangent lines. To find the slope of the tangent line, you look at secant lines, which have slope of f of a plus h, comma b. So that would be kind of the second y value minus f of a b over h. So it's kind of what's changing. And here, notice that the b stays constant. The y is staying constant. The only thing that's changing in this formula are the x coordinates. You go from a plus h and a. And so this is like your old derivative formula, but here I'm letting my y's be constant. I'm just letting my x's change. So there's two variables. Again, you let the limit as h goes to 0. And at the end of the day, you get this thing that we call the partial derivative of f with respect to x at the point AB. Let me rotate, just show it one last time. Maybe this time we'll do it with the surface again. Okay. So notice we're walking along the surface. We're slicing it. We're holding b. So since we're looking for partial derivatives with respect to x, we hold y constant. We hold the other variable constant. Let x change. Y is constant. That gives you these slices. And there's that line of intersection. We're asking, what is the slope along that line? In this animation, we are now looking for the partial derivative with respect to y. And so if we want to find the partial derivative with respect to y, we're going to let x be held constant. And when x is held constant, it's like we're slicing our shape, our watermelon, whatever you want to call it. We're slicing it along the x-axis. So you're like taking, here's that x-axis here at the base, and we're going to slice it right through at x equals a, perpendicular to the x-axis. And every time you slice, you're going to once again get some sort of a a profile cut, right? This black curve. Okay? And we could ask, what are the slopes along that black curve? And finding those would require that we look at the limit of the difference quotient. And when we do that, we find the limit of that difference quotient here. Notice since we're finding the partial derivative, I feel like there's a typo in this. Since there's a typo in this animation right here. This should be f of a plus h, or sorry, f of, oh, never mind. I'm sorry. Getting a little too wild and crazy. I'm overthinking. Pardon me. We're letting our a's, our x's, be constant. These guys are constant. They're not changing. You've got the same thing in both cases. And so that one's constant. And the thing that's changing is the y's. So you got b plus h and you've got b. So those are changing. Why? Because you're taking the partial derivative with respect to y. Let me clear this out, show it again. So if we let our a's vary, remember a is where you're slicing it with respect to the x value, you're going to get different profile shapes, that black curve. And so you pick your a, you slice it, and then we ask, what is the slope along that black curve? Again, where did the black curve come from? It came from slicing through the orange graph, perpendicular to the x-axis. Why is it perpendicular to the x-axis? It's perpendicular to the x-axis because we're looking for the partial derivative with respect to y. So I hope this gives you a better picture of what partial derivatives look like and a sense for why it is that we would hold one variable constant. Example 1b revisited. So if f of xy is equal to 2x cubed, y squared, plus 2y plus 4x, interpret the partial derivative of f with respect to y at 1, 2. So first of all, recall that the partial derivative of y at 1, 2 is 10. The question is, what is that 10? So we need to find the partial derivative, we needed to hold one variable constant. So we're going to hold x constant at x equals 1. Okay. And we know that there is a surface, so we can look at the intersection, the curve where the plane, now you know what the plane is, the plane x equals 1 and the surface f of xy intersect. So this is one of those black lines. This is the black line that's on that that was in the animations. So hold x constant at x equals 1 and look at the curve where the plane x equals 1 and the surface f of xy intersect. Okay. So what we're saying is that, so and this was that black curve in the animation. So what we're saying is that the slope the slope of that curve in the direction parallel to the y-axis. Direction parallel to the y-axis is 10 at the point xy equals 1, 2. Okay, and again, this is the curve. And the reason why it's parallel to the y-axis is because we are looking for a partial derivative with respect to y. Or if we were to think about it kind of like think about derivatives as giving you slopes, and so like a rise over run, what we're saying is that, if you will, kind of like an alternate explanation. If you looked at f of 1, 3 versus f of 1, 2. So notice that I held the x as constant, but I let the y's go up by 1. So the first one would be 10 more than the second one. Why? Because the slope was 10. Similarly, or if you had f of 1, 1 versus f of 1, 2, it's like we're going backwards along a line. Again, we hold the x as constant, we let our y's change by 1, and so we know that the 1, 1 is earlier in the line, so it's backwards along the slope, so it's 10 less than f of 1, 2. And this would be, just to be clear, this would be about, not exactly, about 10 more or 10 less. Notation for first partial derivatives. First partial derivatives of z equals to f of xy with respect to x can be written as follows. You could have the partial derivative of z with respect to x. You could have partial derivative of z with respect to x. You could have the partial derivative of f with respect to x evaluated at xy. The partial derivative of f with respect to x. The partial derivative with respect to x of f of xy. The partial derivative of f with respect to x. The partial derivative of f with respect to x. The first derivative of f with respect to x, I should say, for this last one, it would be the partial derivative with respect to the first variable of f, or last here, the partial derivative of f with respect to the first variable. Similarly, with respect to y, you could have the partial derivative of z with respect to y, partial derivative of z with respect to y, partial derivative of f with respect to y at xy, partial derivative of f with respect to y, partial derivative with respect to y of f of xy, partial derivative of f with respect to y, partial derivative of f with respect to y, the partial derivative of f with respect to the second variable, partial derivative of f with respect to the second variable. So lots and lots and lots of notations for the same thing. Of these notations, the one that we will use the most in this class are probably the partial derivative of z with respect to x, or partial derivative of f with respect to x in a couple of different forms. Okay, so we probably won't be using these last ones, the big D or the first second variable notation. So we won't use much. One simple note about writing, notice that for partial derivatives, we use this kind of funky D. So it's almost like to draw that, imagine doing a kind of a curvy 2, but then getting rid of the little tail at the end. So it's like a curvy 2 with a little loop-de-loop, and then you get rid of the little tail, leaving you with just a funky curvy D. So in this class, when you see curvy Ds, that's going to tell you that you're talking about a partial derivative. When you see a straight up D, that tells you you're looking for a derivative of a single variable function. So partial derivative, curvy D, normal derivative, straight up D. The values of the first partial derivatives at the point A, B are denoted by using kind of like the following notations. So we could say the partial derivative of z with respect to x evaluated at AB. Or you could say the partial derivative of f with respect to x at AB, or the partial derivative with respect to x of f evaluated at AB. So that's 3 different ways of writing this notation. Similarly, you could have the partial derivative of z with respect to y evaluated at AB, the partial derivative of f with respect to y at AB, or the partial derivative with respect to y of f evaluated at AB. To calculate or evaluate an expression such as the partial derivative of f with respect to x at 0, 2, first, differentiate with respect to x, and then evaluate the resulting expression at the point xy equals 0, 2. The concept of a partial derivative can be extended to functions of 3 or more variables. The function w equal to f of xyz has 3 partial derivatives, each of which can be found by holding 2 of the variables constant. Example 2. If z equals x to the 4th sine of xy cubed, find the following. A, the partial derivative of z with respect to x. So here, we are going to let x vary, and we are going to hold y constant. So my x's are going to be allowed to vary, my y's are going to be held constant. So y cubed, you could think about this like a number. Maybe it's the number 7 or something along those lines. And so I have x cubed times sine of something times x. So I'm going to need my product rule. So this will be 4x cubed sine of xy cubed plus x to the 4th times the derivative of sine would be cosine xy cubed. And then remember that for this question, we're treating y cubed as a constant. So this would be like x times 7. Derivative of x times 7 would be just 7 or what have you. And so we're going to have just y cubed as the derivative of that inside function with respect to x. So here you can see the x's showing up. You can also see the y's aren't changing. Those are being held constant throughout this particular partial derivative. Similarly, if we want to find the partial derivative of z with respect to y, now we're going to let y vary, and we're going to treat x like it's a constant. And so in this case, the x to the 4th out front is a constant. And so we will have x to the 4th. The derivative of sine is again cosine, x y cubed. and we're treating x like as a constant. So this would be like constant times y cubed. We're using the chain rule. So we'd have the constant, which is x, times the derivative of the y cubed, which would be 3y squared. Here's our constant in this case. And here the y cubed would be our variable. And so the parts that are changing are the parts that have y's in them. So here is your partial derivative of z with respect to y. Again, the first gives you the slopes in the x direction. And the second gives you the slopes in the y direction. X direction, in the y direction. In the first case, we held y constant. And in the second case, we held x constant. Higher order partial derivatives. You can differentiate a function more than once to find partial derivatives of second, third, or even higher order. Second partial derivatives of z equal to f of xy. So we can take the derivative twice with respect to x. And so you have the partial derivative with respect to x, and then we take the partial derivative a second time with respect to x, which we would write as the second derivative of f with respect to x twice, or the partial derivative of f with respect to x, and then with respect to x again. If we were doing this with respect to y, you have the partial derivative of f with respect to y, and then you take the partial derivative with respect to y again, or the second partial of f with respect to y twice, or you could think about this as the second partial of f with respect to y and y, or fyy, if you will. That's all fine and dandy. Things get a little bit more interesting when we have first a partial derivative with respect to x, so that's the partial derivative of f with respect to x, and then with respect to y. So partial derivative with respect to y of the yellow partial derivative with respect to x. You would notate this as the second partial derivative of f with respect to x first, and then with respect to y. So notice the first partial in this notation is written second. Or you could write it as fxy, where the first partial derivative is the first subscript and the second partial is the second subscript. So notice that the order of in which things are written is different. We could look at the first partial with respect to y and then with respect to x. So you'd first find the partial derivative with respect to y, and then you would find the partial derivative with respect to x. You could also write this as the second partial derivative of f, first with respect to y, and then with respect to x. In the other notation, it would be fyx. And so you would first take the partial derivative with respect to y, and then with respect to x. So the main thing that I need you to notice is that the two notations, Leibniz notation and the F notation, that they list those second partials in the reverse order. So in Leibniz notation here, Leibniz notation, you're reading from right to left, and the reason you're reading from right to left is because of kind of how we would implement the Leibniz notation. So you would read right to left. But in the F notation here, F notation, we would read left to right. It's not hard, you just sort of have to keep the two straight. Notice that these last two cases where you have a partial derivative with respect and one with respect to y, so there's two different variables involved, are called the mixed partials or the mixed partial derivatives. So once again, caution. Notice that the order in which x and y are listed in the mixed partials in the two notations is different. In Leibniz notation, the order reminds us of the process, whereas with the subscripts, the order matches the order of the partials. So in one case, it helps us with process. In the other case, it helps us with order. Partial derivatives of order 3 or higher can also be defined. For example, f of x, y, y would be like think about your order. Here we're reading left to right. And so that would be like saying, find f, x, y, and then take another partial derivative with respect to y. Or it would say, first, find a partial derivative with respect to x, then find a partial derivative with respect to y, and then find a partial derivative with respect to y again. Or you could think about this as the third partial derivative of f, first with respect to x, and then twice over with respect to y. It's just notation. You just got to learn what it means and how to navigate it. Example 3. Find the second order partial derivatives of f of xy equal to x squared y cubed plus x to the fourth y. So the first thing that we need is we need fx and fy. So fx, maybe I'll write it this time as xy will equal, here we'll hold the y as constant. So we'll have 2x y cubed plus 4x cubed y. So I treated the y as like a constant, found my derivative with respect to x. I could also find fy. I'll try to use different notations here. So fy would be 3x squared y squared plus x to the fourth. Here I treated y like a variable and x like a constant. So those are my first partials. Now I've got to find my second partials. So I could find my second partial fxx of xy. So this would be the second partial now with respect to x. And so I'm going to start with that first partial. Its derivative is 2 times y cubed plus, ooh, this is funny. I wrote a subscript when I meant a superscript. Plus 12 x squared y. Or we could find f of x, but secondly, I could find the partial derivative with respect to y, and that would be, again, refer back up to the top, and take the partial derivative with respect to y, treating x like a constant, y like the variable. So here I would have 6x y squared plus 4x cubed. So those are two second partials, but now with respect to now one with respect xx and the other with xy. On the other side, let's write these with the Leibniz notation. So we could have the second partial of f with respect to y. So they're both with respect to y. Here, I treat y like it's the variable, x like it's the constant. So I'll still have 6 x squared y plus 0. Or I could we already have the partial derivative of f with respect to y. Now I could find the partial of that with respect to x, because I'm looking for mixed partials. So this would be the second partial of f with respect to y, then x. Here I'm reading right to left. So now I want to treat x like it's the variable, y like it's a constant. So I'll have 6x y squared plus 4x cubed. So multiple notations for partial derivatives, second partial derivatives, or second order partial derivatives. And I want to note in particular that at the bottom we have f of xy, and we also have f of yx. And I want to point out that f of xy is equal to f of yx. So those two are the same. So this leads me to Clairaut's theorem. Clairaut's theorem says, assuming f is defined on an open set D of R2, and that f of xy and f of yx are continuous, notice that those are the mixed partials, but in reversed order, and that they're continuous throughout D, then f of xy equals f of yx at all points of D. So it tells us that the mixed partials are equal if everything is nice. Mixed partials are equal. Example 4, let f of xy equal y squared e to the x plus y, and find f x y y. So to do this, first we need to find fx. So fx will be y squared e to the x plus 0, because we're treating y like it's a constant, or just y squared e to the x. So we've dealt with the x. So next up, we want to find fxy. So we're trying to deal with this y in the middle. And so here, we look at the derivative of the result above, and we take its derivative with respect to y, treating x like a constant. We'll have 2y e to the x. And then lastly, we want to find fxyy. So here we're looking for our derivative with respect to the second y. And once again, we treat x like it's a constant. We take our partial derivative with respect to y, treating y like the variable, and we'll have 2e to the x. And that is the third partial derivative with respect to x, then y, then y. Or you might write this as fxy of x, y. Example 5. If f of xyz equals x squared cosine z sine y, find the third partial derivative of f with respect to x, then y, then y. So here we're doing a question very similar to the one above. We're just using our Leibniz notation. So again, we'll start by trying to find the partial derivative of f with respect to x. So we start on the right side in this notation. So this will be we're treating z like a constant and y like a constant. X is our only variable. So we would have 2x cosine z sine y. So now we want to find our partial derivative with respect to y. So this would be the partial derivative with respect to y of partial derivative of f with respect to x, or the second partial of f with respect to x, then y. And so to find it, we just take the partial derivative with respect to y of the blue line, and we'll treat x and z as though they're constant. The derivative of sine is cosine, so we'll have 2x cosine z times the cosine of y. Because the only thing that was changing was y. Derivative of sine y would be cosine y. Last but not least, we want to find our partial derivative with respect to y again. So this would be the partial derivative with respect to y of second partial of f with respect to x, then y, or third partial derivative of f with respect to x, and then with respect to y twice over. So once again, we treat x like a constant, z like a constant. The only thing that's changing is our y's. The derivative of cosine y would be negative sine y. It's both negative 2x cosine z times the sine of y. And here it's that second y that is changing throughout. Example 6. Suppose that a point Q moves along the intersection of the sphere x squared plus y squared plus z squared equals 1 with the plane x equals 2/3. At what rate is z changing with respect to y when the point is at 2/3, 1/3, 2/3? We don't need a picture, but sometimes a picture can help. So let's think about it. So we have a sphere. It looks something like this. And then we're going to, and the sphere has radius 1 and it's centered at the origin. And so then we're going to slice this thing with some sort of a plane when x equals 2/3. And so there's going to be some other like profile bit right here when x equals 2/3. Here's that 2/3, and so we're asking what's happening along this this blue circle. So this is x equals 2/3, and we're trying to figure out. Looks like our at what rate is z changing? It looks like our slope will be something like this, and so just based on the picture, we're assuming that we would have a negative slope. But let's see how it all plays out. So to find this, we have x squared plus y squared plus z squared equals 1. We could solve for our z to put things in a more familiar form. So z would equal the square root of 1 minus x squared plus y squared. Sorry, 1x squared minus y squared. And technically, this is a plus or minus. But since we're in the foreground, we have positive, everything is going to be positive. We're above the xy plane. We know that we're going to take the positive root here. So the question is, at what rate is z changing with respect to y? And so that tells us that we want to find z sub y, or the partial derivative of z with respect to y. So z with respect to y will equal the derivative of a square root, which would be 1 over 2 times the root times the derivative of the inside function, treating x like a constant and y like the variable. That would be a minus 2y. So we could clean this thing up. So the 2's will cancel. And so all told, we are left with zy being equal to negative y divided by the square root of 1 minus x squared minus y squared. And we're asked to evaluate this when x is 2/3 and y is 1/3. So we just need to do a little bit of arithmetic. Let's see, what's that going to be? So that would be negative, that's telling us that zy would equal negative 1/3 divided by the square root of 1 minus 4/9 minus 1/9. So that would be 9/9 minus 4/9 minus 1/9, or just 4/9. So this is minus 1/3 divided by the square root of 4/9, which is 2/3, or negative 1/2. We're not surprised to see the negative, because we were expecting to find a negative. So this negative 1/2 would be the slope of this tangent line. So at what rate of change is z changing with respect to y when the point is 2/3, 1/3, 2/3? Z is changing at a rate of negative 1/2 at that point. So having been through this lesson on partial derivatives, I hope you can see what I was alluding to at the front end. Finding partial derivatives is pretty straightforward. It just requires holding one or more variables constant and treating just one of the variables as an actual varying variable. So letting one change. So the process is really easy. The one part of this that's challenging is the notation. And so I encourage you to think about and be careful with your notation, paying special attention to when you're using the Leibniz notation and when you're using the subscript notation. We will use both notations through the remainder of this course, and also through any subsequent multivariable calculus classes that you have. So being familiar with both notations will be very advantageous to you. So I hope that's helpful to you, and may you have a wonderful day, or at least a partially wonderful day. Take care.